Hey, sorry, the introduction is missing, but Victoria Yaneva is going to give us a wonderful talk now.
Yes. Can you all see my screen properly? Slideshow is working?
Yes.
Okay, great. Well, thank you, Matthias, for the nice words, and thank you for having me here. I am certainly very excited to be giving this talk at Boston College, and I want to say right from the beginning, if you have any questions, if something is not clear, please feel free to interrupt and to ask your question. I won't be able to monitor the chat as I speak, but I am sure that in the Q&A portion at the end we can address these questions. And as I mentioned while we were waiting for people to gather, I am always very happy to hear from people with any questions, whether these are related to NLP in assessment or whether these are related to, hey, what you do at NBME? How is your summer internship program coming along? We are, going to post something about that soon. We are inviting students who are at least in the second year of their PhD programs to apply. So please do reach out with any questions like that. And I also appreciate you all being here as it is lunchtime. It's quite a good turnout for that time of the day. Now, Matthias said a few words about what I do at NBME. So NBME stands for National Board of Medical Examiners. We're based in Philadelphia. If anyone wants to practice medicine in the United States, they need to obtain a license. And currently the way to obtain such license is to pass the United States Medical Licensing Examination, which is developed and administered between NBME and the Federation of State Medical Boards. Now, what is the connection between NLP and what we do at NBME, meaning being a testing organization? Well, we work on several problems. So one of these is the automated scoring of free text responses. In the past, this has been automated scoring of clinical patient notes that the examinee is right in response to questions, or this is now free text responses to novel item types that don't follow the multiple choice format that need to be scored automatically. So this is one application that we are interested in. The second one, most broadly, is automated item generation as well as technology-assisted item writing. Does anyone want to chime in with the guesses of what's the difference between the two? It's all right, you don't have to. People are busy having lunch. So when we talk about automated item generation, the goal here is to produce an item fully automatically, the whole item. Whether this is through some sort of template-based item generation or an NLP-based item generation, where you have a neural network model generating the item, we are talking about, full automation. While technology-assisted item writing is certainly a great area of interest as well, given how challenging fully automated item generation is, where here we still have human item writers writing, for example, the stem. They know the correct answer, but they have an NLP engine suggesting distractors that they can choose or ignore. And this really helps with one of the biggest bottlenecks in item writing, and that is selecting high quality distractors and doing that process more efficiently. So that is one application in addition to automated scoring. And finally, predicting item characteristics, just as another example. I shouldn't have said finally, I'm sure there are more applications there. This is the scenario that we are going to talk about today. We are going to use predicting item characteristics as a test bed for the item representation approaches that we're going to discuss today. So why are we interested in predicting item characteristics such as difficulty or response time simply using the item text? And the reasons that I can quote here are two. The first one is that any form of automated item generation would need some sort of evaluation. And if we end up with a large number of items, such as ones produced using templates, we need some sort of filtering of how should we select from these large numbers of items ones that we should pre-test. So here, having some way to predict difficulty or discrimination would be very, very helpful. Or even embedding these predictions at the generation stage, so that we can generate items with a desired level of difficulty, could be another application of these approaches. And of course, the second big application of why we want to have predicted item characteristics is that when we do pre-testing, we have a limited number of pre-testing slots, and we want to have a way of assigning our most promising items to these pre-testing slots so that we increase the probability of a larger number of items surviving pre-testing. So if we are able to select items that have the desired level of difficulty, response time, discrimination, and assign these items to the slots, we would have higher survival rates and better quality assessments. So with these applications in mind that just give a broad idea of what a testing organization might want to use NLP for, let's focus on today's talk and what you will know at the end of it. The biggest part of the talk aims to provide understanding of the different approaches to text representation and their evolution through time. And when we talk about their evolution through time here, it's not because we are so much concerned with the historical aspects of NLP, but because that historical evolution also coincides with increasing abstraction. So as we follow how the ideas developed, we go to more and more sophisticated approaches that have been developed through the years. And we are also going to contextualize that knowledge in a few experiments of predicting item characteristics from item text, where we are going to discuss some practical consideration around developing these models. So if you were to implement something like that for a problem that you're interested in that requires representing text, and you want to build NLP models for it, what kind of things should you be thinking about? So for example, what kind of training data would you need? How can you optimize the use of that training data? What amount of context may need to be encoded? Should we have discussions about model interpretability here, and so on and so forth? So this is really intended more so as a practical guide than as something that presents conclusive results on predicting item characteristics. And now I'm going to pause here for any questions so far, and if we don't have any, we can move on with the problem formulation. Do we see anything in the chat? No? All good. So let's take a look at this example of a practice item from one of our clinical exams. We see here that the STEM presents the clinical case of a 16-year-old boy. We have 5 answer options, only one of them is correct, answer option A. And our goal here is to predict how difficult this item is in terms of proportion correct responses, and how long on average would it take to respond to this item in seconds. And so one of our options here is to go to expert item writers and ask them, how difficult is this? How long would it take? And experience has shown that these predictions or guesses based on their intuition are not very accurate. So what we are left at is to try to extract some sort of a signal contained in the item text that would be predictive of item difficulty or item response time. And now let's pause here for a moment and imagine that this was a reading passage in a reading comprehension test. And we wanted to determine the reading difficulty of that passage. We would probably want to know what is the average sentence length, because we know that long sentences are harder to comprehend, or we would want to know what's the average word length, because longer words tend to be more complex. And so we could use these predictors where NLP is very good at capturing them and they are very highly correlated with reading difficulties. So this would be a more or less easier task compared to what we are trying to do here, because here our items don't vary in terms of reading difficulty. In fact, special precautions are taken that this doesn't happen and that they only vary in the difficulty of the construct they measure. So here we are not talking about surface characteristics of the item that make it more or less easy to read and to understand, but we are talking about conceptual difficulty. And another reason why this task is so challenging here is that our sample of examinees who are responding to this item, they are very highly able, they have self-selected through being very successful at school, passing exams to enter medical school, passing their subject exams at medical school. So here we have a highly proficient sample. And so the variance in p-values or item difficulties is not very big. So this really makes our problem very, very challenging. And we are looking at ways where we can use NLP to extract signal that can, improve the prediction. Now, let's start with ways in which we can represent the item that we just saw into some sort of a numerical vector that can be used as input for a machine learning model that predicts difficulty or response time. I find these linguistic representations best represented as a staircase like this, where at the bottom step we have the most simplistic approaches, such as bag of words, one-hot encodings, TF-IDF, where here the idea is, for example, for one-hot encoding, we take all of the words in our items, and we put a 0 next to each word that co-occurs with another word. Sorry, we put a 1 next to a word that co-occurs with another word, or a 0 if they don't co-occur next to each other. And so we end up with a very long and sparse vector with many zeros. That is somewhat helpful in making predictions and representing the text numerically, but is a very, very basic item representation, very intuitive one though. So in trying to capture more refined information, the NLP field was largely focused on human-engineered linguistic features in the 90s and large part of the early 2000s, before a shift occurred towards using embeddings around 2013. And we are going to focus on these three stages mainly: the human-engineered linguistic features, non-contextualized, and then contextualized embeddings. And before I explain what we mean by non-contextualized and by embeddings and by contextualized embeddings, we are first going to focus on the human-engineered linguistic features. Now, there are two requirements here to extract these features. So the first requirement is to have an initial hypothesis that a given feature will co-vary with a variable of interest. So if I was trying to predict the difficulty of a reading passage, I would extract average sentence length as a predictor because I have some hypothesis that this will help me predict reading difficulty, right? If I didn't have that hypothesis, if I didn't think that that would help, I probably would not, write code to extract that feature, to extract that predictor. And the second requirement is that we need to have the necessary NLP tools and resources for extracting that predictor. So if I wanted to extract average sentence length, I would need to have a parser and a tokenizer that would help me actually process the text and extract that information. And let's elaborate a little bit on what we mean by this. Let's see example features at several levels of linguistic processing. So an example of a lexical feature would be average word length in syllables, or complex word count. This is usually words with more than 3 syllables. Example of syntactic feature would be part of speech count, average sentence length. Example of a semantic feature would be polysemous word count, or number of words with more than one meaning. And so how can we extract this information? So for part of speech count, we need an automated part of speech tagger. And fortunately, at this stage, for the English language, these part-of-speech taggers have high accuracy, I think around maybe 98%. But this wasn't always the case. And to develop these tools, we had to go through a very long and laborious process of developing resources like the pen tree bank, where humans would label by hand parts of speech and their relationships and all that. And it is also important to note here that there are many languages around the world that are under-resourced, where we don't have enough data, or we don't have enough tools, or tools with high enough accuracy to be able to straightforward extract that type of information. Another feature that I like giving up as an example is the polysemous word count. So how can we automatically determine whether a word has more than one meaning or not? Well, in this paradigm of linguistic feature extraction, this would be done most likely by looking into WORDNet. And what is WORDNet? It is an ontology. So it is a resource where in the span of decades, humans would annotate the relationships between words, such as chair is a type of furniture, and so on. So you can imagine how laborious and time-consuming and resource-consuming this process is of actually mapping out the semantic relationships between words in this manner. So here, if we have the word bank as a classic example, we would determine that this word is polysemous because we would find it in different places in the WORDNet ontology, where in one place it is linked to a financial institution, and in the other place it is linked to a river, for example. So this is all very helpful and a very transparent way of representing text, because we know exactly what aspect of the text we measure, but it suffers certain limitations. And the first of these limitations is that because they're hypothesis-driven, linguistic features may not always capture the most important or relevant predictors in a data set. So if we don't know what in our clinical item text is most predictive of its difficulty, then we can't set out to extract that. And secondly, what we already alluded to is that we are limited by the coverage quality and availability of NLP tools and resources such as ontologies, parsers, etc. And these two are two very serious limitations for extracting linguistic features. Now, let's imagine for a moment that there was a data-driven approach to extracting linguistic signal, something that we don't have to set out to seek, a predictor based on a hypothesis and thinking what might work and might not work, but the data, mined in a certain way, represented in a certain way, can help us identify what works and what doesn't. And secondly, what if we could infer the semantic, syntactic, or pragmatic properties of words without having to rely on external resources such as ontologies? So it is these two questions that address the two main limitations of linguistic features that were addressed by the shift to embeddings around 2013. So what happened then? WORDZVEC was introduced by a couple of papers, and this started this whole, something that is referred to as a revolution in NLP. So let's say a few words about what embeddings are and what we mean by non-contextualized. Let's consider these two sentences. He filled the Wampy mug with the substance, passed it around, and we all drank some. And the second sentence is, we found a little hairy Wampy mug sleeping behind the tree. Should I ask you what you think Wampy mug means? Are there any volunteers who like to share? We don't have to, because we know what the participants in this experiment said. Matthias, did you have a guess?
I don't really dare to say what I'm thinking here.
Well, now I'm interested. Okay, so even though Wampy mug is a nonce word and it doesn't really mean anything, All of the participants in the experiment were able to say that in the first sentence it referred to some sort of a liquid container, while in the second sentence it referred to some sort of an animate creature, like maybe a small animal. And what this shows us is that here, if we replace the word wompimak in the first sentence with another nonce word, we would still be able to infer, its meaning based on the context that the words appear in. And we would probably all still agree that this is a container that contains liquid. And this is really the theory behind embeddings. So it's called the distributional hypothesis, that words which occur in the same context tend to have similar meanings. And this is also later immortalized by a very famous phrase that you may have heard: "You shall know a word by the company it keeps." So it is that idea that even though you may not know what wompimak means, you can infer its meaning by the surrounding context. And the good news here is that context can be represented numerically by encoding word co-occurrences in large collections of texts. So we call a collection of text a corpus, and the plural is corpora. So here, if we have enough data, and by enough I mean really a lot of data, we can encode these co-occurrences. And this already reminds us of these one-hot encodings that we mentioned at the beginning, where we have a very sparse vector containing zeros and ones, depending on whether two words are neighbors. And so this wouldn't be very helpful here, because we're going to basically have a vast matrix about the vocabulary in a language that mainly contains zeros. So the trick behind embeddings is to use a neural network model to condense this huge and sparse matrix into a matrix with something like 300 dimensions or 1018 dimensions that consist of dense word vector representations. So instead of having many zeros, we're going to have 300 numbers that it's not a sparse vector, but they actually mean something because of the way they encode that context. And this is all done using various, deep neural network models. And so the distributional hypothesis and what we saw in terms of theory behind embeddings was all developed in the 50s, 60s. So why did we become successful at, implementing embeddings only in the past several years? Well, it's practically feasible thanks to two advances. The first one is the accumulation of large amounts of electronically stored data, because these are very data-hungry models. We really need a lot of data. And the second advance is the developments in parallel computing, which provide the computational power needed to process these large data sets. So again, when we talk about the carbon footprint of NLP nowadays, we mean the amount of, computing that needs to happen in order for us to create these very large models. Now, what do we mean by non-contextualized or contextualized embeddings? Let's take a look at these two sentences. I read Simon's book, which was hard, and Simon hit me with his book, which was hard. When we talk about the earlier type of non-contextualized embeddings, for example, Word2Vec, we would have the same embedding for the word hard in both sentences, regardless of the fact that in the first case, it represents something that is solid. In the first case, it represents something that is challenging or difficult. And in the case that follows, it represents something that is solid. While after 2018, with more modern models, we would have slightly different embeddings for the same word, depending of its difference in meaning in different contexts. And that is the main key difference there. So that's how we distinguish between the two types. Now, let's take a look again on non-contextualized embeddings, but not just the theoretical underpinnings behind them, but let's take an example such as Word2Vec and see how it works. So here, another great advantage is that if we were just extracting linguistic features, we would extract these for the data set of items that we possess, and that would be all the information we have. While here we can use a large corpus of external texts, extract the embeddings, and then apply them to our items, even though it's a lot less text there. So we utilize that external information that it comes from a larger data set for our problem. And so to generate the embeddings using such data, we have two distinct stages. The first one is data generation, and the second one is model training. I find it very helpful to separate the two when we explain this process. So let's focus on data generation first and go to our favorite NLP phrase, you shall know a word by the company it keeps. Now here we have pre-processed this sentence by removing stop words such as a and the, and we're left with you shall know a word by company it keeps. Now let's say we want to generate embeddings for the input word no. And we have a sliding window of size 2 that takes the two words preceding the input word no and the two words following. So what this looks like is a data set like this, where in the first column we have our input word no, and in the second column we have each word from the sliding window before or after our input word. After that, we are going to move on to the next word as an input word, in this case, the word word. And we are going to have output words, the two words before it and the two words after it. And in the third column, we're going to put a label of whether the two words are neighbors or not. So one marks neighbors. And the whole idea here is that we would want to predict if the two words are neighbors, given the first word as an input and the second word as an output. And this is all very exciting, but we have a problem here, right? The problem is that we only have, by definition of the approach we use, we only have words that are neighbors in our data set. So we don't have any examples of label 0, of non-neighbor words. So we resolve this by introducing the so-called negative sampling. So here we are going to sample words using specific approaches that are actually not neighbors of the words that we are looking at, such as the first word in the English dictionary, the aardvark. It is not a neighbor of the word no in our corpus, so we put it a label 0. And now we have a data set here that contains some words that are neighbors and some pairs of words that are not neighbors. And we are going to use a neural network to predict whether they're neighbors or not neighbors. And how can we do this? So we need to represent numerically the word no in some way, and we need to represent the word you, the output word, in some way. How do we do that? Well, we initialize two matrices. The first one would store the embeddings of the input word no, so we call that an embedding matrix. And the second one would store the embeddings of the output word, so we call this an output matrix. And we initialize these with random numbers, completely random to begin with. And the size of these matrices is m by n, where m is the number of words in the corpus. So here every row would be no, and all of the words that we want to create embeddings for. And then n is the number of dimensions of the embedding. So for WORDZVEC, most famously would be 300. Now these can be determined empirically, how many dimensions we use, but let's not worry about that part for the moment. Let's say that we stick to 300. And so we have these random numbers in our matrices, and we create a training sample for the input word no. So we take one positive sample and one negative sample. And what this means is that we have one input embedding and 3 output embeddings here, right? And now this is going to be the more technical part that we are not going to focus on in great detail, but I urge you to check the paper. Here, the similarity between each input word and output word can be quantified by the dot product of each input word and output word embedding pair. And once we have that dot product, each of these 3 dot products can be transformed into a value ranging between 0 and 1 using the sigmoid function. And then finally, these probabilities are subtracted from their target value, yielding errors. So what does this look like? We have our data here, like input word, output word, target. And then we have some sort of a model prediction using these random numbers in the matrices. And then if we subtract the model prediction from the true target label, we get the error. So once we have that error vector here, we are going to iteratively go back to our matrices and use the error vector to update the weights of the two matrices. So these are no longer completely random numbers, they're slightly adjusted numbers. And then we go to the whole process again and again and again, while at the end we end up not just with random numbers, but with weights. And so this would depend on our computational resources, how many iterations we can have. But essentially what happens after training is complete is that each input word, so we discard the output matrix and we only care about input words, which has, each input word has a word2vec embedding with the required number of dimensions. Does this make sense so far? Okay. So this would be our word2vec embedding here. Now, we talked about non-contextualized embeddings and gave the example with word2vec. Now, what about contextualized embeddings? And I'm sure many of you have heard about the BERT model and what it is. So BERT is one of the biggest models and probably most prominent models for contextualized embeddings that exist and are used nowadays. And it was originally released in two versions, BERT base and BERT large. And I have put here just a pointer to the number of parameters in the base model, which is more than 110 million parameters for that neural network. And for the BERT large, that's more than 300 million parameters. So just to give you some context about how gargantuous these models really are. And now let's say just a few words without going into great detail about what BERT does. And the main difference with word2vec here is that it produces two different kinds of embeddings. The first one is token embeddings, and the second one is sentence embeddings. So embeddings for an entire sentence, not just a word. Let's take a look at the token embeddings first and say why we say token embeddings and not just word embeddings. Well, it's because what word2vec does is that it chops the words into subwords and then generates embeddings based on the co-occurrences of these subwords. And what this really helps us with is that if in the test, when we're trying to make an inference, if we see a word that did not appear originally in the training data, but can be constructed based on the subwords that we have embeddings for, then we can create an embedding for that word based on the based on the subword embeddings. While this is not something that we can do, for example, with word2vec. If word2vec encounters a new word that it hasn't seen before, there is just no embedding for that word. So this is why this is really helpful here. So we are talking about subword units when we talk about token embeddings. Now for the sentence embeddings, the task here is to determine the sequence of two sentences. Does sentence B follow sentence A? And the rationale behind creating embeddings like this for whole sentences is the fact that it captures larger context and longer dependencies. And this has been proven useful for many downstream tasks. And there are many variations of BERT. Just a few to mention. So you may have heard of DistillBERT. So it reduces the size of BERT by 40% while retaining 97% of its language understanding capabilities and being much faster. So then we have Roberto, for example, which has improved hyperparameter tuning. Importantly, we have many BERT models that were pre-trained on various domain-specific texts. So what happens if I want to take a look at my items and I want to use BERT to predict their difficulty? I can take a model that somebody else pre-trained on the entire PubMed and Medline abstracts database, and take that pre-trained model, fine-tune it on my small data, and make predictions that are supposedly much better than starting from scratch or starting from a model that is trained on generic data. So there is quite a few models out there that people have released that are pre-trained on domain-specific data. And I don't want to leave people with the impression that we're only using BERT nowadays, even though it really is very widely used. You may have heard about other models such as GPT-2, GPT-3, T5, Electra, PaLM, DiBerta, and really, I feel that with every major NLP conference that comes, and they come probably every 3 or 4 months, we have a new state-of-the-art model, a new thing that beats the previous thing, a bigger model. So it really is, the field is growing to an extent where one of the most popular tracks in NLP conferences at the moment is dedicated to actually creating smaller models that are efficient. So efficient NLP is a topic at the moment. Now that we have a primer around linguistic features, non-contextualized embeddings, and a very brief explanation of contextualized embeddings, it's time to focus on some experiments. Now, let's go back to our favorite example, our clinical multiple choice question that we saw at the beginning. And remember that our task here is to represent this text numerically such that we extract signal from it that helps us predict proportion correct responses, item difficulty, or the average time it took our examinee sample to respond to this item in seconds. So to do this, we first extract a total of 113 linguistic features. And these vary from lexical, syntactic, semantic, readability, cognitive, frequency-based features based on word frequencies, and so on and so forth. There is a lot of creativity that can go into a process like this. And here, for example, if you take a look at the readability features, we don't expect that they would bring value to the prediction because we said that the items are written to avoid differences in reading difficulty. But it is possible that when this variable interacts with another variable, that this could amplify the signal. So this is our first type of predictors, the linguistic features. Then we extract embeddings, and we do this in several different ways. First, we extract WORDZVEC using generic data. And by generic data here, we mean the book corpus, which contains 800 million words, and the entire English Wikipedia, which contains 2,500 million words. And we want to compare that, for example, to BERT base, which is also trained on this generic data. In addition to BERT base trained on generic data, we also train BERT large trained on this generic data because we want to see if the difference in the size of the model contributes to a better performance. In addition to that, we have BERT base trained on generic data, and we now also train BERT base based on clinical data, which is PubMed Central and Medline abstracts. And here we want to see if the domain of the data actually has an effect on the performance, given that we have the same model just trained on different data. And finally, we also have Roberta, which has improved hyperparameter tuning compared to BERT. And we trained that again on the clinical data, and we want to see whether Roberta performs better than BERT-based clinical when trained on the same data. And for all of these BERT embeddings, we extract token level embeddings and we extract sentence level embeddings. And we want to see whether, these different extracting different amount of context in this way has an effect on the results. And so, drum roll. These are the results for proportion of correct responses. We can see the pink dots above there, the 0R baseline. And what this simply means is that we take the mean value of the item difficulty in the training set, and we assign it as a prediction to the test set. And this is how we compute the root mean squared error for this baseline. We also experimented with many different types of models. A few of them only are presented here. And we saw that random forests with 400 trees outperform many other models. Finally, we see here that the random forest results actually outperform the baseline with statistically significant difference. Now, here is where we talk about difference between statistical significance and practical significance, because the quality of these predictions is still needs to be improved for them to practically help us solve the problem of improved pretesting or evaluation of automatically generated multiple choice questions. But what this shows us is that there is some signal there that the model captures. And we can see that the best result is the one by BERT-based clinical sentence. So BERT-based model trained on the clinical data using sentence level embeddings. And it is very interesting to note that, when we use token level embeddings from the exact same model, we don't have this advantage that we notice here. Now let's move on to predicting response time, where we are in general a lot more successful in terms of practical significance. We can again see that random forest performs better, but this time we don't see such a huge difference with a clear advantage for one model over the others. We can say that linguistic features did not perform very well, and we can certainly say that BERT-based clinical sentence is again one of the best performing models here. So what does this mean in terms of practical considerations when developing such models? Well, we know that the BERT-based clinical sentence model is the best performing configuration across both experiments. So the fact that training on generic data did not replicate this performance shows that for our domain, there was superior performance for domain-specific data, in this case, the clinical data. And this is interesting and consistent with results from the literature, where Gu and al. Experimented with extracting embeddings for the clinical domain using generic data, using clinical data, or a mixture of the two. And they found that there was a clear advantage for the medical data, and that general domain or the mixture of the two actually harmed performance. And so one could speculate that there is some negative transfer that occurs here between the two domains. So learning something on the generic domain actually is not always helpful when applied to the clinical domain. In terms of model size effects, we didn't see a clear advantage for BERT large over BERT base when trained on the same data. And we also didn't see a clear advantage for Roberta over BERT-based clinical when trained on the same data. So my comment here would be that there is no straightforward way of deciding which architecture is best for a given task. It's an empirical question, but bigger and more robustly optimized models are not necessarily always the best performing ones. In terms of amount of context encoded, so predicting item difficulty benefited from encoding longer context and longer dependencies. BERT-based clinical sentence significantly outperformed BERT-based clinical token. And I find this very interesting here. So why did sentence embeddings from Roberta perform consistently worse than those from BERT? And we can trace this back to a modification introduced in Roberta, where they changed the task for next sentence prediction. So they modified that task, and it looks like this did affect results in our context. But overall, we could say that reasoning about the relationship between pairs of sentences does seem important for predicting item characteristics. And in terms of model interpretability, something that the assessment field is traditionally always concerned with, we can ask the question whether model interpretability is important when predicting item characteristics. And I think one could make an argument that it is not as important as in maybe other applications, and that here what we care about is having accurate predictions, even if they come from black box models. And should interpretability be the focus, then linguistic features clearly have the advantage here, right? Because they can provide greater insight into the relationships between various interpretable characteristics of the items and the outcomes of interest. Now, in terms of limitations, there are several that we can point here, and they're mainly around things that we could have done to improve the results, but we didn't. So again, our goal here is to illustrate the use of these approaches to text representation to a problem of interest, but we could extend this work to combining different predictor types within a single model. So we could concatenate embeddings, for example. We can experiment with many other types of embedding models, and importantly, we chose to use random forests and to feed the embeddings into it as predictors, but we could actually fine-tune the models, and that could also improve performance. So if you plan to ever experiment on your own data sets and problems of interest, these are all things that you can do to improve the results. And as a conclusion, at least within the domain of clinical multiple choice questions, it is beneficial to pre-train models on biomedical text. And when this is done, encoding larger context and longer dependencies can improve results. And at the same time, using larger models or ones with improved hyperparameter tuning does not always necessarily lead to improved predictions. So lots of empirical questions here and lots of things to experiment with. This is all for today, and I am very happy to hear your questions.
Yeah, let's thank our speaker first. So thank you so much. It was extremely interesting and really ask questions. I'm sure there are some.
Hi, this is Henry Brown. I have a question. Can you hear me?
Yes.
Thank you very much. Very, very interesting. And I'm just wondering here, to what extent the clinical embeddings capture the complexity of the medical scenario, and are the measures of difficulty, to what extent they agree with the expert's opinion of the complexity of the situation. For example, the number of symptoms that are included in the scenario, the degree to which the symptoms are perhaps somewhat inconsistent, et cetera, et cetera. Whatever the experts who are developing the scenario are thinking about in terms of creating a realistic medical scenario.
Mm-hmm. Excellent question. So the first part of it, to what extent the clinical embeddings capture the conceptual difficulty, it's an empirical question. That's why we try to predict difficulty. Yeah. As to the second part of the question of whether we can actually develop some quantifiers of difficulty based on what the item writers or the experts think, such as number of symptoms or, quantify ambiguity in some way. As far as I'm aware, previous attempts to do that in the literature have not really resulted in very accurate estimates, which is why we resort to pretesting and we resort to all of these a lot more elaborate ways to determine difficulty, because the answer is that as humans, we are very bad at judging this. And it really also depends on the sample of test takers.
Right. So my last question is, what is the strength of the correlation between the predicted difficulty using these methods and the empirical difficulty based on student performance?
So R squared, I have to see the exact number because I focused on root mean squared error there.
Yeah, right.
As something that we try to minimize, but I can dig this out and share it. I think because this is, by the way, based on a book chapter for a book that Matthias and I are editing on NLP in assessment.
Right.
There is also a manuscript that comes with this talk, should you wish to read further.
Okay. Thank you very much, Victoria.
Yeah.
There's a discount, Henry. Other questions?
There is a question in the chat, it seems.
Let's go to the I don't see anything in the chat.
Okay, I'm going to. Oh, sorry, it is a direct message.
Okay.
Okay. Neuroscientists would have us believe that we are learning a lot about human perception by the ways in which AI is processing information. For example, understanding that much of vision is prediction and hypothesis testing rather than passive absorption. On a basic level, do you feel there are insights for better understanding how human beings read based on this research? That's actually, I love this question, and I wish I had an answer to it. And I think that the parallels between, for example, neural network models and human processing are very, how to say, the more we learn about neural networks, the more inspired we are to form new hypotheses about human processing, and the more we learn about human processing, the more inspired we are to learn to refine neural network models. And what this really reminds me of is how there is a paradigm in NLP research where people look at embeddings and fMRI data, and basically they're trying to see if there is some correlations there. And it is an extremely complex problem because of the curse of dimensionality. So because of fMRI data resulting in so many vectors corresponding to different locations of the brain, we are always able to use that data in some encoding experiments or decoding experiments where we show some success. So I don't think we have some, functional MRI. I don't think we have some conclusive results there, just because empirically it's so difficult to have a conclusive answer to a question like that. But it is a very, very interesting field, I would say. And we have also more data sets that become available to look exactly at problems like this.
Yeah, I think this is really inspiring. But as we know, or now have seen again, predicting item difficulty is really non-trivial and has many different aspects. Are there other questions? Which, by the way, also holds for the human side. So I think we have mental models, what makes things difficult, and we have a long tradition, not only in item writing, also if you think about teachers' expectations in classrooms, what should be easy, what should be difficult. So we are very often failing in terms of how we predict what should actually be self-evident, etc. So I think it's interesting to have these many different perspectives here.
Also difficult for whom is the very big question there.
Other questions? Chat. I have a quick one. So I think Henry also tapped into that a little bit. So you're essentially only using the item as it is. You're not using any metadata, any annotations in terms of content or subdomain, anything in terms of does this thing have additional stuff, such as graphic or an audio or something like that? Do you use that?
We have in the past, and we have a whole paper that specifically looks in a lot more detail into predicting response time. And we did use metadata there, such as the domain and whether or not the item contained a picture of some sort or not. And what was interesting, as far as I remember from this study, is that previous research had found a lot of high predicting power of whether the item contains an image or not. But in our case, it seems that this was accounted for by the interaction of different features. So I don't remember having this predictor added to the model really boosting performance or anything like that. But if you look at it as an individual predictor, I think it was one of the more salient ones.
Thank you. So, last chance. We have one more slot for another question.
Is this the article?
Going twice. Have you? Well, then let's thank our speaker again. This was really brilliant, and it's really very. And you, oh yeah, you allow.
So just a quick question. This is not the article that I referenced, even though we look at these things as well. I will put a link in the chat to the article I referenced in just 1 second, and it also looks at fairness. Implications for fairness from predicting response times.
Perfect. Thank you so much. Great. So then, this was our second talk. Very exciting. Thanks again, and see you in a month, I guess.
Thank you, everyone, and thank you again, Matthias.
Thank you, Victoria. Very good.
Bye.
Bye-bye. Mm.